Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you all for coming. I'd like to introduce Tara Matthews, who's a graduate student at UC Berkeley, just finishing up her PhD, and she's giving a talk this morning on designing and evaluating glanceable peripheral displays. So welcome.
Thank you. And thank you for coming. An overarching theme in my research is in helping people feel in control of their disparate tasks and the many pieces of information that they're presented with. There's lots of information that's requested of people, like, for example, interruptions for your location while you're mobile, and that's presented to people. For example, information from all the tasks that you're balancing at once. How can we design technology to help users feel in control of their many tasks and the large amounts of information they see? My past work and future interests span a wide range of research areas that are related to this theme, from support in the daily life to support at work. I'll briefly introduce a past project on location privacy, and then I'll spend most of my time presenting my dissertation work on designing and evaluating glanceable peripheral displays to support multitasking. And I'll finish up by describing a second project on assistive technology for the deaf, and by discussing my future interests in health and activity management. As an example of helping people feel in control of task and information overload, in a past project I looked at location privacy preferences to social relations. Location services can be valuable, but location requests are yet another interruption that people have to deal with. Is it possible to automate location disclosure, and if so, under what conditions? And if not, how do we design these systems to help people feel in control of their privacy and also balance the interruptions and the valuable services they provide? To answer these questions, I worked with researchers at Intel Research Seattle during an internship to conduct an exploratory field study. Our study was 3 phases. The first and the last were in the lab, where we asked about people's preferences for location disclosure before and after the field study. And then we did a 2-week experience sampling field study. And experience sampling is a method where people are periodically sent a questionnaire that asks about their current opinions and thoughts during their current situation. Our questions included 4 hypothetical requests for location that were customized to be from people that they knew. And we probed their reactions to these requests. Can we automate location disclosure? When asked after the study, 6 users said yes, 4 said sometimes, and 6 said no. And asked a different way, how do you feel about automatic location disclosure? The results indicate that 10 people would be open to this, depending on who the requester was and what their current situation was, and 4 would not. We gathered a lot of interesting data with implications on how to design location-enhanced systems that enable people to feel in control of their privacy, but also to balance interruptions. To give you an overview, I'll share 2 highlights. First, we learned what factors a location disclosure depends on. First, people wanted to know who the requester was, why the person was requesting, and they would ask themselves, do I want to share right now? So this depended on users' relationship with the requester at the time, their current activity, and sometimes even their mood. So some of these things would be hard to sense, which would make automation more difficult. Another interesting finding is that once users chose to disclose, they wanted to disclose what was most useful to the requester. So for example, if the requester was from another state, they would send maybe city, because that would be more meaningful than an exact address. If the user was not willing to share this information, they simply chose not to disclose. And this was a departure from some suggestions in past research that people would choose different location details or levels of detail to protect their privacy. Overall, these findings help us to design location-enhanced systems that better balance our need for privacy control, less interruptions, and the valuable new services that they provide. Next, I'll present my thesis work, which focuses on addressing people's needs for more control over their many work tasks. Multitasking is a part of the way we work. For example, it's important to make progress on longer-term tasks, shorter daily tasks, but also to address the needs that coworkers bring to us each day. However, there are serious problems with fragmenting our work with constant interruptions, like I am, and task switches, like to email. The average information worker balances 10 tasks at once, spends 3 minutes on a task before interruption, and is interrupted 1 time per task. These interruptions can harm productivity. On top of that, we're inundated with tons of visual information. It isn't easy to monitor secondary tasks from, like email, or to get back into tasks when we resume working on them. What can we do to help users feel in control of these frazzled multitasking situations? In my work, I show that peripheral displays can help users to quickly get information about tasks and interruptions without losing their task flow, and it helps users to control interruptions. A major research question I tackle is, how do we design peripheral displays to improve multitasking for information workers? This question is the basis of my thesis work. To answer it, I began with interviews of peripheral display creators and an activity theory analysis of peripheral display use. I will only talk briefly about the activity theory analysis in the interest of time. And then I conducted 3 experiments to gather design knowledge, which I'll present in depth. What is a peripheral display? It's a tool used primarily for quick and easy information awareness that's monitored while you're doing other things. It's used primarily at the operation level, as defined in activity theory, or with routinized automatic behaviors. For example, say you're working on 3 tasks. You're collaborating on a document online, you're fixing bugs in code, and you're checking email. You're fixing bugs while you're waiting for your colleague to finish editing a passage that you just talked about. And you're also getting about 2 emails a minute, one of which might be those conference reviews that you're waiting for. And so you're monitoring these tasks in these 3 windows. These windows are not designed to be easily monitored. There's so much detail. Where do you look? What's changed? What's important? Imagine a display that lets you monitor these tasks fluidly without breaking your concentration. You can see exactly what's changed to both best use your time and your colleagues' time. Peripheral displays let you control your own attention, highlighting useful information. This work aims to provide design and evaluation guidance. I realized that peripheral displays were difficult to create and tried to understand why by interviewing 10 peripheral display creators. The results were that there's no clear definition or terminology for peripheral displays. People were using lots of different terms like ambient, notification, peripheral, and they were using them differently. Also, there's a need for design knowledge and evaluation criteria and guidelines. I address all of these in my thesis, but today I'm going to focus on sharing work gathering design knowledge. I worked with 2 grad students to develop a theoretical framework for understanding, designing, and evaluating peripheral displays using activity theory. One contribution of this framework was identifying 3 types of tasks that peripheral displays typically support: primary, secondary, and pending. By primary task displays support tasks that you're focusing on right now. So for example, a weather display that's helping an air traffic controller monitor weather changes. Secondary and pending task displays are both not related to the primary task. With secondary, you're monitoring mainly just for information. So for example, an office worker monitoring a weather display. With pending, you're monitoring the status of tasks that you've set aside with the intent to switch back to it. So pending task displays show a lot of promise for supporting multitasking. Results of a study I ran show that peripheral displays like these can significantly improve users' efficiency and satisfaction while multitasking by showing them information that helps them to keep track of all their pending tasks. These are 3 versions of a peripheral display to show task information. One is mini windows, clippings of relevant portions of task windows, and borders that highlight changed content. For those of you who aren't familiar with this, which do you think will be most effective? Would anybody like to hazard a guess?
Can you explain to me what you mean by borders?
Anytime something changes in the window that it's around, it appears. The green part appears.
Can you explain where these are shown?
Sorry, they're in the periphery. They sit on the edge of your screen.
So they're on the main, it's a single monitor configuration. They're on the main monitor, not on a secondary monitor?
It could be on the main monitor, on a secondary monitor, on the edges. What's that?
Aren't those totally different situations?
Yes. All right. So imagine they're on the left side of your primary monitor.
Imagine whether they are on the left or the right side.
Okay. Well, I'll move on for now. And I will answer this question in much more detail in the multitasking study, which looks at how different peripheral display designs affect multitasking efficiency. Peripheral displays can be any modality, but I'm interested in information visualization, so I'm studying visual displays. Peripheral displays that people are building right now use a huge range of visuals, from highly abstract pictures to text. But there isn't much guidance on which visuals are most effective. Peripheral displays are not like traditional graphical user interfaces. We need more design knowledge for how to design these displays that tend not to be the focus of your attention and are always used while you're doing other things. These peripheral displays all show task-related information. One thing is similar about these displays. They all abstract information. So they reduce detail, they extract the most essential information, and they transform information to new forms. But which of them abstracts information most effectively? My research addresses this question, focusing on how to abstract information to be glanceable. The Unlearn and Learn studies look at this question in depth. What makes peripheral displays glanceable? Given this introduction, the goal of my thesis is to increase knowledge on how to design and evaluate glanceable peripheral displays to improve the user's experience and efficiency while multitasking. Notice that glanceable and multitasking are key parts that distinguish this work. By glanceable, I mean enabling quick and cognitively easy intake of visual information. Designers tend to accomplish glanceability by abstracting information. The contributions of my thesis are showing that peripheral displays can improve overloaded multitasking situations for users and concrete advice for designing glanceable displays. So next I'll present the multitasking study, which examines the first question about peripheral design for multitasking. In this study, we explored the effects of different abstraction techniques used in peripheral displays on multitasking needs that were well documented in the literature. First, keeping your concentration on what you're doing. Second, knowing when to go back to tasks and being able to easily get back into tasks when you restart them. What is abstraction? It's defined differently in various fields, but for peripheral displays, it's been defined in past research as reducing detail, like reducing the detail on this photograph of John Lennon, extracting features, like pulling out the most recognizable features in this sketch, and transforming information into new forms, like replacing the entire photograph with the Beatles record label logo. With glanceable peripheral displays, the goal is to make information easier to intake, ultimately reducing information overload. In this study, we compared 3 abstraction techniques on 4 different peripheral displays. So the first one was scaling, or shrinking down a version of all the content. The Uploads task cluster, shown here, sits on the edge of your screen and helps you to monitor this task. The mini windows update in real time. The benefit of this is that you get big overall changes and you see the spatial layout of the window, and the downside is that none of the content is legible. The next type of abstraction is pulling out and showing just the most relevant task information. And we do this by cutting out a relevant portion of each task window that is coupled with an application icon, like the Excel clipping shown here. These clippings are arranged into task clusters in the peripheral areas, and clusters are called clipping lists. So the benefit of this is that you're showing just the most relevant information, and the downside is that there's a lot of details and there could be a lot of text. Yes?
How do you decide what is relevant?
Sorry, what was that?
How do you decide what is relevant?
So that's up to the user. They would select a portion of the window that they wanted to monitor. Finally, the last version is change detection. These two displays add colored change borders to windows with changed content. This is a really simple cue, but it doesn't add a lot of information. We added change borders to both the scaled version and the clipping lists. And so these are the 4 peripheral displays we compared in our study. Which will most improve multitasking efficiency? This diagram shows the setup for our study. The peripheral displays we studied were all based on the Scalable Fabric Task Management System, which was developed right here at Microsoft Research. We used Scalable Fabric because a past study showed that it was effective for helping people manage tasks when compared to Windows taskbar. But in the past study, the visual design of the peripheral display had not been studied, not studied in depth. This shows our study setup. So we had Scalable Fabric on 2 different monitors. The middle area was the focal area where you would do your work, and the remaining tasks were set in the periphery where shrunken versions of the windows would help you to monitor them. So this is the scaled version of the peripheral display. Again, we studied 3 modifications. So the clipping list could change the way these mini windows looked, and the change borders could be added to them. These were the 4 task clusters that we studied, and these tasks were designed to mimic real-world tasks that had the user switching between tasks as they waited for emails, documents to upload, and pages to process. We measured how quickly they finished all the tasks, how often they switched between windows and tasks, and the accuracy of their task switches. For example, did they switch to email when they got a spam message? Our participants were 26 users from the Seattle area who had moderate to high experience using computers and office-style applications. Our major result was that clipping lists were the most effective for all of our metrics. Why is this surprising? It's because the clippings are higher in detail than the change borders. You would think that they would require more attention and cause information overload. The reason it works is that the clippings show enough relevant task information. Though the change borders didn't always improve performance, they did further improve performance when added to the clipping lists. Overall, we learned that this type of display can actually improve multitasking performance. And the most important point for abstracting information is to show enough relevant task information, even if that means more detailed visuals. But using visuals that are quick and easy to identify further improves performance. So this display performed the best because it made task information visible and easier to understand, indicating that glanceability is important. Recall that glanceability means enabling quick and easy intake of visual information. All of these displays, yeah?
Can you tell me if the change borders actually affected the performance and the scaling?
They negatively affected the performance because the content wasn't legible, but yet there was a change indicated. So for any case when the change wasn't something that really required them to switch tasks, they would switch tasks and it would be a wasted effort. So all of these displays are fairly complex. We can improve their glanceability, further increasing multitasking efficiency and reducing information overload. But how do we design for better glanceability? In this experiment, we studied only a few visuals. We need to study a bigger space. And also we need to measure just the glance, just the time to interpret visuals without attention capture or other confounds mixed in. We do this by keeping stimulus onset and size constant. The next two experiments explore this question in depth. What abstractions are most glanceable? There are a few key questions that are relevant to a study of abstractions. First, it's commonly believed that simple peripheral display visuals are better, but is there such a thing as too simple, like when you're trying to convey lots of information? These are simple renditions that were used in the Scope Notification Manager built right here at Microsoft Research. They show calendar, email, task, and alerting information. Is this glanceable? And if we were to substitute in pictures for this, would that be more glanceable or less? Also, can designers convey enough information to maintain user efficiency with simple visuals, which may be less capable of conveying as much information than more visually complex designs? The last study showed that multitasking performance could be improved when enough relevant task information was shown, so this is an important trade-off. Finally, should designers always intuitively convey their intended meaning to users without training, as is commonly believed? I call this a trade-off between low and high symbolism, where symbolism is the ability to convey common meanings. For example, this is the InfoCanvas display that was built at Georgia Tech. It's showing many different information streams, and the user has to remember the abstract mappings. And there's 11 total mappings in all that they have to remember when they're using this. The number of mappings may affect glanceability, which is something that I study. Understanding glanceability requires knowing how to abstract information. For peripheral displays, this typically involves two key characteristics. First, complexity, or the amount of visual detail. So here it ranges from simple or more abstract, like the stick figures, to complex or less abstract, like the photograph. And then symbolism, which is the ability to convey common meaning. Here it ranges from low symbolism or more abstract, like the abstract art, to high symbolism or less abstract, like the word coworker. In the studies, we study a range of it from low to high symbolism, but I refer to the endpoints most often as low and high symbolism. So low symbolism means an arbitrary mapping. The user is not likely to guess the meaning of the sign without training. Or as Saussure said, there's no inherent, essential, transparent, self-evident, or natural connection between the signifier and the signified. But that doesn't mean that it can't be learned. With this definition, Saussure was referring to the connection between written words and their meaning. But we classify words as high symbolism because they're already really highly learned to the point where they have meaning to people. And then the other end of the spectrum is high symbolism, more meaningful or interpretable. Complexity and symbolism are two continuous characteristics that create a design space for peripheral displays. Existing displays are all over this space. So, for example, the InfoCanvas display is low symbolism and complex. I see to hear display, it's a sound display for the deaf, is simple and low symbolism. Clipping lists are complex and high symbolism. And the I am buddy status on Sideshow is high symbolism and simple. While there are other factors that designers may be considering, like aesthetics and privacy, it's important to understand how these trade-offs affect glanceability so designers can make informed decisions.
Just a quick clarification question. When you're talking about symbolism here, is it inherently contextual then? Is basically, it seems like you're leveraging what the previous knowledge of whatever your audience is, and that has to be taken into account to, it's not under like a latent variable in your taxonomy.
So you would want to look at your audience for the display and see what makes sense to that audience. So definitely.
Okay, thanks.
I ran 2 dual task experiments to understand what characteristics make abstract renditions glanceable. The first study is the unlearned study, which compares renditions that the users have never seen, and the learned study, which compares renditions that the users have learned to identify in cohesive sets of 3 or 7. The contributions of these studies are advice for the design and evaluation of glanceable displays that are intended to help designers create better peripheral displays to support multitasking. This work is grounded in a large body of work in psychology, human factors, and HCI. Psychology literature has provided theories of attention which help us to understand which visual features are processed with the least effort. For example, pop-out may help with information overload since it helps you to zero in on important information. Other studies have compared text versus pictures, color versus simple graphics, and color set size. Icon design studies have looked at issues that are related to my work, like complexity and concreteness, but most have focused on recognizable icon function relationships, not supporting automatic secondary task monitoring, which may benefit from lower symbolism renditions. Here I'd like to highlight some distinguishing features of my experiments that show gaps in past literature and also highlight the contributions. I explore the impact of different renditions that are inspired by existing displays for information monitoring, that represent the entire abstraction design space, that are organized into cohesive sets, so sets with similar symbolism, complexity, and style, and are of different set sizes, that are well-learned or unlearned, and they're all used in divided attention situations. I began with a design exploration, and here my goal was to select sets of renditions that demonstrate the major trade-offs in glanceable design, so complexity, symbolism, and set size. To understand the techniques that designers currently use to accomplish glanceability, I interviewed 9 designers, and they emphasized the importance of abstraction and talked with me about that concept. And also they encouraged me to study a wide range of visuals, so not just really simple ones, but also more complex ones. I decided to design for email because it's a real task that could benefit from a peripheral display that helps users control the interruptions and information overload that can be caused by new messages. I used sender group based on results of an email usage study, which showed that they're one of the more important factors in deciding when to read an email. So though there are other important pieces of information that help with that decision, I decided to pick one. I worked with 2 professors of design at Carnegie Mellon to derive our renditions. We used stock photos, clip art, and some that we created, and we referred to design theory, semiotics, and our interviews with designers and also existing displays to gather 32 sets of renditions. And these are 4 examples to give you an idea of what they looked like. The cartoons are complex high symbolism. The abstract art are complex low symbolism. Stick figures are simple high symbolism, and this bathing suit lady are simple low symbolism. And that was based on a display, the InfoCanvas display that was actually taken straight from that display. I also varied the renditions on, oh, go ahead.
Did you also run just as a baseline, just the text version?
Yes, we did text as well. Yeah.
Sorry, why would you, it seems like the ideal is always simple high symbolism. Why is that not the ideal?
I will present results on that. There are situations when it's not ideal. And I can give you a preview. It has to do with when you increase the set size significantly.
Increase the what?
Set size. So when you include more renditions.
Well, I assume as you include more, then the value of each one starts to move toward low symbol. I mean, maybe the mapping becomes arbitrary the more. It's a higher cognitive effort. More
To figure out what things are. It turns out that more detail helps to distinguish, to add meaning as the set sizes get bigger.
So do you have sort of a formula? Like if I need, 20 things, where I should be on that detail scale?
I don't have a formula for you. The study, we studied 2 set sizes, so we have some basic guidelines based on that. Oh, okay. So I also varied the renditions on subject and technique. Subject was based on a semiotics classification of signs. Here the subject is people and the techniques is illustration. To give you another example, the subject here is situations or ideas, and the technique is photos for the complex ones and illustrations for the simple ones. Other subjects were objects and text. To narrow down the renditions into control for style, we pre-tested with 10 users using a survey and a pilot of the study that I will present to you next. We measured identification accuracy and speed and user ratings. And the results showed that symbolism and complexity led to significant results for many of our metrics, but that subject and technique did not, so we decided to remove them from consideration to help us to prune our set. A factor analysis of the different ratings that we looked at resulted in 3 factors driven by interpretability, aesthetics, and likelihood to adopt. So these were the ratings that we used in our study. And the results also helped us to choose these 14 sets. And so I'm showing just the coworker rendition for each set here. We chose these because they had the highest accuracy and ratings amongst other renditions that were located similarly in the space. Here we chose 6 simple sets, 6 complex, 2 text, 3 low symbolism, 3 medium symbolism, and 6 high symbolism. And we categorized by the symbolism level using the accuracy of people's identification. So there were significant differences across the groups, but not within them. We use these renditions in our 2 experiments as follows. So for the unlearned study, we had users identify renditions in all 14 sets with no training. In the learned study, we had people memorize and identify either 3 or 7 renditions in 4 of the sets that did particularly well. And this diagram shows the dual task setup for both of our experiments. Our primary task was a classic continuous manual tracking task based on work by Wickens. Though this task lacks ecological validity to what an information worker would do, it better enabled us to control that the user had a primary task that had constant visual and cognitive demands. And this was really important for the internal validity of our metrics. With this task, the red circle would move around, and it was moved by software, and the user would have to keep the blue cursor inside the red circle. And going outside the red circle was considered an error. So they would be tracking, and then a rendition would show up on the peripheral display, and they would identify it by pressing, so this one is standing for family, so they would push the family key on the keyboard. Yeah?
So the difficulty of that primary task depends on the speed that you're moving the red circle. How did you decide how difficult to make that?
We had it set at a constant rate, and then we would vary the size of the circle based on the error rates. So we wanted to have, we were concerned about people getting tired by the end, because we found in pilot testing that by the end of the study people were making a lot of errors, a lot more errors than at the beginning. And so we would increase the size if they were making a lot of errors. So it was a constant, so we would decrease it if they were doing really well. So it was a kind of a constant difficulty rate. Okay, so they continue.
So a question related to that is that you might expect that the error rate would be related to the difficulty of the secondary tasks as well. So if your secondary task is getting really hard, and you start making it easier to get to, and then you vary something to be able to get easier on the secondary task, because assuming you've randomized the items that are showing up with the secondary task, right?
Yeah.
So how quickly were you varying this difficulty of the primary task?
We had it happening gradually, so we would check over an interval of 30 seconds, and we would gradually change the size of the circle so that it interfered with the secondary task as little as possible, and interfered with their ability to do the primary task as little as possible. So we wanted to create a constant challenge, but not to interfere with the secondary task. And so error time was a metric for us, but we were concerned that error time would not, that there would be some issues with it, partially because of that, and partially also because maybe they make the error when they press the key instead of when they look at the display. So we did a redundant measure, which was glance time, where we used video coding to do this, but we would look at the actual amount of time they looked at displays and the amount of reaction time to actually identify displays. So we also used that as a metric of how long it took people to interpret. Okay. So just to continue, they continued tracking. Another rendition showed up. This one stands for stranger, so they pushed the stranger key on the keyboard. And we had a mask over the keyboard so they could only see and push certain keys. Our measures for both experiments, we split them up into performance and qualitative. For performance, we measured reaction time, which is the time from when the rendition appeared to when the user identified it. And we split that up into 2 different measures. First, peripheral processing time, which is the time from when the rendition appeared to when they first looked at it, and glance time, which is the time from when they first looked at it to when they identified it. And we measured those using video coding. We also measured the correct identification rates, the primary task error times, and the proportion of views that used peripheral vision alone. And for qualitative, we got the users' ratings of different sets and the overall rendition preferences. Our participants for the Unlearned study were 26 users, aged 19 to 41, all had a lot of computer use experience and they checked their email often. For the Learned study, it was similar demographics, but we had 49 users split up into 2 between subjects groups. In the Unlearned study, we asked the question, what factors affect how quickly users can interpret renditions that they've never seen? Our design was within subjects, so all the subjects saw all the renditions. We had 14 sets with coworker, family, and stranger renditions in them. And the renditions were varied on symbolism, so low, medium, high, and text. And for this we used a single factor ANOVA with 4 levels and LSD post hoc tests. Our method began with 5 minutes of dual task practice. Then we began the dual task study proper, where the user would do the circle task while identifying 42 renditions that they'd never seen before. And then we had them do a qualitative survey where they rated each rendition set 1 to 5 on interpretability, aesthetics, and likelihood to adopt. And then we had the user select 2 favorite sets and 1 least favorite set. An important purpose of this study was to categorize our renditions into symbolism levels. Our correct identification results helped us to do this. As shown here, there were significant differences across the groups but not within them. Overall, our result was that all metrics improved for higher symbolism and are best for text. This general result is not too surprising because going into the study, the renditions were unlearned. These graphs illustrate the same idea, which is that, so all of these show a significant effect for symbolism. As symbolism increases, glance, error, and peripheral processing times decrease, and qualitative ratings increase. Some interesting things to point out here. First, these time differences, though significant, are small. The largest one is less than a second. But the qualitative ratings are quite large, up to 2.5 points on a 5-point scale. So the biggest effect was not in performance, but in qualitative ratings and user opinions.
What's the difference between the dotted line and the purple line?
The dotted line is the interpretation rating, and the solid line is the likelihood to adopt rating. To see how our metrics related, we computed a factor analysis using rendition set as the unit of observation. A factor analysis takes a large number of variables and summarizes them into a smaller number of factors that contain variables that are related. Ours reduced 7 variables to 2 factors that explained 82% of the variance. Our first factor had large loadings from all of our metrics except aesthetics. And the second factor was driven by aesthetics. We believe that the phenomenon underlying factor 1 is glanceability. Both our performance and qualitative metrics, except aesthetics, are strongly related to this factor, which suggests that a qualitative approach would be highly useful to predict glanceability. This would save designers time by eliminating the need to gather performance metrics. When unlearned, high symbolism renditions were favored, except the celebrity photo. The least favorites were abstract art and the high symbolism photo. These graphs give you a sense for the interpretation and adoption ratings that each got. The interpretation ratings are on the left, adoption ratings on the right, ratings 0 to 5. And as you can see, these photos stand out as anomalies. Like we would expect them to be switched if they followed what the ratings for the rest of the renditions, the pattern for the rest of the renditions. These results lead to a surprise, which is that the photos of people led to very low performance and ratings compared to other high symbolism renditions.
These are clip-out photos.
Yeah.
So
it's not coworkers, it's some abstract coworkers.
Yeah. Mm-hmm.
And the stranger is, well, still a stranger. Okay.
Yeah. That one
the
fits.
family is a
Stranger family, as opposed to your family.
Stranger family. So, like you said, we theorized that these models who are not the user's coworker, family, and so on may have interfered with the interpretation somehow. People had no problems associating cartoons of people, and even the celebrity photos got higher user ratings. Perhaps because they're beautiful, and perhaps because they're more removed from the actual likenesses of social relations. So we believe that interference effects are important to consider when you're choosing photographs, but more work is needed to understand the underlying reason for these.
I'm also wondering, I mean, these photos seem a lot different from the celebrity photos. I mean, the backgrounds are really different. I mean, you've got these really nice headshots for the celebrities, etc.
Yeah.
It seems like that alone could be a fairly significant difference.
Yeah. Yeah, it's a little bit harder to convey a group of people like a family. So that's definitely a consideration. So next is the LEARN study, which looks at what factors affect how quickly users identify renditions that they've memorized, and what is the effect of increasing the number of renditions. We have the same dual task set up in metrics, but a different design and method. So the between subjects factor is set size. Half the people learned 3 renditions per set, coworker, family, and stranger, and half the users memorized all of them, 7 per set. The study included 2 sub-designs. First, we wanted to know the effect of complexity, so we compared simple versus complex versus text, where they were all high symbolism. For this, we used a 3x2 ANOVA. And we also wanted to understand the effects of symbolism, so we compared low versus high symbolism, where both were simple. And for this, we used a 2x2 ANOVA. The method for this study began with a shape memory test. This was a standard test, psychological test to see how well people remembered shapes. And we balanced the scores across our 2 between subjects groups. Then we did 5 minutes of dual task practice, and then users began the study proper, where they would, for each rendition set, they would go through a training session where they trained until they became fluent. So they would identify renditions in the set until each was identified correctly 5 times in a row. And then they did the dual task, where they played the circle game and identified each of the renditions 3 times on the peripheral display. And then they did that for all 4 sets. And then they did a qualitative survey, where they rated each rendition set 1 to 5 on our 3 qualitative rating metrics. And then we had them rank the sets 1st to 4th favorite. All the results that I'm going to present here are significant unless I say otherwise. So the first results for symbolism. Symbolism had no effect on performance when learned. And this was unlike the last study, where symbolism was the main effect. As you can see from the graph, there's no difference between these 2. However, symbolism does affect qualitative ratings. The lower symbolism renditions got lower ratings than the high symbolism renditions. And this leads to the first surprise for this study, which is the simplest renditions were not favored. I hypothesized beforehand that when learned, the colored squares, which were the simplest and the most distinguishable, would lead to the best performance and ratings for set size 3. However, users preferred the black and white picture, even though these 2 led to similar performance. Users explained that it's hard to remember what color represents what. I found this surprising because there were only 3 colors to remember. One more point. This indicates that low symbolism renditions may have a harder time gaining approval despite greater simplicity and similar performance. Results for complexity depended on set size. When few were learned, simple are best. So as you can see here, they had faster reaction times and higher qualitative ratings. When learned, simplicity also led to the best performance, but not the highest qualitative ratings. Notice that the black and white's ratings went down and the cartoon's ratings went up. And this leads to a second surprise, which is that complex renditions led to good user opinions for the larger set size. This is especially surprising since the cartoons led to worse performance. Users explained that it's not as easy to remember what icon corresponds with which group of people with the black and white picture. And for the cartoon, it's easier to identify and relate with as they pictorially represent the categories, and They are the most pleasing to look at and not as boring as the others. These results indicate that the extra detail may make renditions more attractive and identification easier with larger sets.
But this will change depending on the size of what you're displaying, right? If you're showing a smaller rendition of a more complex picture, it's not going to give you more. It's probably going to give you less.
Yeah, that's actually a really interesting question. We had the sizes all constant, so they were all 1 1/4 inches on their longest side. So they were all the same size. But you're right that if you shrunk down a photograph to very, very small, people wouldn't be able to distinguish it. Another surprise for this study was heavy use of peripheral vision. People used peripheral vision alone quite a lot in this study. So 39% of viewings used peripheral vision alone in the LEARN study. Another surprise is that color supported this really well. This graph shows the percentage of views that used only peripheral vision. And for set size 3, you can see 90% of the colored square viewings were peripheral. This is surprising because prior research recommends not using color in the periphery because our color discrimination is poor there. But on our dual monitor setup with the peripheral display close enough and the color large enough, users were able to distinguish the color just fine in their periphery. And this is useful information for people designing for single and dual monitor systems where the peripheral display may be close enough. Yeah?
How did you measure whether it was a peripheral glance?
We used video coding and we watched the people's eyes. So we could see it when they looked at the display or not. And the way we...
On the peripheral display?
Yeah, the way we set it up was we had the camera in front of the user pointed at their face, and we had a large mirror behind them that showed when the peripheral display updated. Okay. So both studies contribute to this last surprise, which is that the impact of glanceable visuals on peripheral display monitoring performance was minimal, but on user satisfaction is significant. I expected the performance and satisfaction results to be more closely parallel. The time saved between renditions was small, less than a second. So for 50 emails a day, that's not going to make a real impact on your performance. Though note that we did select the best performers from our pre-testing and from our first study, so we couldn't expect big differences for this task. Despite this, glanceability still was important to people. For example, the black and white picture got higher ratings than the colored square despite similar performance. Overall, we recommend that designers take these qualitative ratings seriously. Based on these results, I've distilled a few best practices for...
Can I stop you before you go into the best practices piece?
I just want you to, can you go back like just 3 or 4 slides to your preference ratings? The list of, went back from that. Oh, one more. Sorry. There we go. Do you have any of the data on the same kind of ratings for text?
Text. Oh, the identification and adoption ratings?
Yeah.
I do. I didn't show them because they didn't show the interaction effect as well on the graph. It made it a little more cluttered. But
I'm just
I wish I had
that
it.
seems to be the
One that's not like everybody else, right? And if you've changed, if the sizes are all the same, and you've shown in some of the earlier studies that text seems to do very, very well. And so I'm just curious what people's opinions are for that. Right?
Yeah, I wish I had put that in an extra slide, but the text was usually somewhere in between but a little lower. So, for example, you might expect the dot to be right about here on this graph and right about here on this graph. So it didn't really do all that well,
Okay.
really. But it wasn't significantly lower than either of them either.
Okay.
Okay, so I've distilled some best practices for evaluating and designing glanceable peripheral displays. First, for evaluation, glanceability of unlearned visuals may be evaluated qualitatively following realistic usage, and listen to user preferences. For design, use low symbolism renditions with caution, Sorry. So that was the example of the square. Simple renditions are highly effective for peripheral vision. Color can be effective for displays on single and dual monitor systems. And again, this depends on the proximity to the focal area and the size. Extra visual detail may make renditions more appealing and identification easier within larger sets. This was the example of the cartoon. And consider interference effects when choosing photographs to represent certain information. I'd like to emphasize that these best practices help to narrow down what to study. Because we had to limit the number of renditions that we looked at, we can't recommend exact levels of complexity and symbolism for different set sizes, which was Daniel's question. We do have these qualitative guidelines for getting much closer to picking effective designs to study. Also note that the closer your system's goals are to the ones that we studied, the better the results will apply. So these are best applicable to displays for divided attention, performance-oriented information monitoring situations. Why are these results important? Peripheral displays have the opportunity to change the way we multitask. Imagine an interface that lets you monitor, maintain your focus on what you're doing, keep up to date on all the other tasks that you're monitoring, and easily transition between tasks. The results of the first study show that peripheral displays can improve all these multitasking needs for users, and the second and third studies give concrete advice for designing and evaluating glanceable peripheral displays. This work leads, yes?
Another question on the, following up on what Ann said. When you started the study, what just your own intuition, which of the different designs would you have deployed in if you were in a situation where you could choose one? And at the end of the study, I mean, it looks like all of them have pros and cons. What's your intuition? Which one do you like best now of the ones that you tested?
Of the four sets, which one do I prefer the best?
Fragmenting, right? The text one is one as well.
I think that for most information, you have larger set sizes. Usually you're not going to have just a couple of things to convey to users. So I think it's important to have higher symbolism designs. And my intuition is that things like color, which I thought beforehand would be really effective in smaller set sizes because you don't have to remember much and it's right there. I mean, it's very easy to perceive. Might be better for redundant coding and for highlighting. So to add color to different renditions to make them more distinguishable helps them pop out, but to convey meaning with it is a little bit harder.
How do you feel about the text rendition?
The text rendition?
Yeah.
Again, I think redundancy is useful there. So text is really good for conveying information and helping people to not have to learn something. But it's not as glanceable just to look at. So to add color to it, to add a picture to it, to put things together, I think is probably...
Maybe like a combination with the training wheels, you would have the word on it, and then that it would be colorful, and so people would use that to learn the colors. And
yeah. And to help it pop out to them. Yeah. So this work leads to some interesting future work opportunities. First, we know that showing the most relevant task information is important from the multitasking study. But for different tasks, what is the most important information? If we could determine common information that people use for certain applications or for certain tasks, we could create peripheral views of applications or activities. For example, this email display could be what you see when your email application is not visible. Also, how do we combine renditions and maintain glanceability? For the scope display, it combines lots of simple visuals to create a more complex one, and it uses spatial layout to also add additional meaning. And finally, a next step could be to conduct field studies to determine what the impact of the effects we saw in the lab are on people in real work settings. To summarize, the main contributions of my thesis are to provide knowledge for designing and evaluating glanceable peripheral displays to support multitasking. And I contribute a definition and common terminology for referring to peripheral displays. A major finding was that peripheral displays that show enough relevant task information can improve multitasking needs. And Finally, I contribute best practices to provide concrete advice for designing and evaluating glanceable peripheral displays. These findings contribute to the larger research theme of helping users feel in control of their many tasks and information overload. I'd like to conclude by sharing my past research on assistive technology for the deaf that also contributes to this area, and then my future interests. Sounds give us tons of information about our environment, from an awareness of people's activities and movements to important alerts like the phone ringing or kids crying. Sounds are also critical for communication. People who are deaf must overload other senses like visual or haptic channels to maintain an awareness of what's going on around them and to communicate. Peripheral displays can help by making sound awareness easier to get. One of my projects was to design, build, and evaluate peripheral displays of non-speech sounds like the ones pictured here. I also conducted need-finding interviews with 8 people who are deaf and found that a major unaddressed need was awareness of both speech and non-speech sounds in any location. So we created a mobile tool to address this need. It provides text transcriptions of the last 30 seconds of audio upon a user request. And so like the diagram shows, people would carry around a PDA and say they missed something. They wanted to hear or know what just happened. They push the button and the last 30 seconds of audio would be sent to a human transcriber who would transcribe it and send it back to them in a text message. We conducted a 2-week field study of this working prototype with 6 representative users. And our major result was that users were very excited by the tool and found a number of valuable uses for it. For example, the most exciting thing for them was that the tool enabled them to fill in chunks of conversation that they often missed. They also used it for announcements in public places, when using machines with voices, and to describe environmental sounds like traffic. In the future, I'm really interested in research related to health and activity management. Activity management, also called task management, is based on the idea that we should organize work the way people think about it, by activities, not by applications. Some benefits of this approach are that technology will be better suited to support multitasking, time management, automatic activity documentation, and work reuse, all of which could help people feel in control of their many activities. Existing work has looked at aggregating activity resources and enhancing window management, like the scalable fabric display. Also enabling users to move activities between different devices, activity reuse through patterns, and peripheral awareness of activities like my dissertation work. There has been a real interest in the research community in breaking out of the desktop metaphor, and activities are a good place to start to focus new UI research. There are a number of hard problems to address. First, activities are high level. They're hard to define, and they include many resources. We don't know what an optimal activity-centric system looks like because the existing desktop computers are centered on applications in a different metaphor. Glanceability will help in designing these complex UIs, but it will also be important to look at and incorporate new structures, visualizations, and interactions. Second, managing the tools, resources, and metadata for an activity is a lot of extra work. What can we automate? And for tasks that we can't automate, how can we make the interactions really lightweight? I'd like to collaborate with AI researchers on this problem on designing usable systems that address user activity management needs. For example, the Swish and Seer projects here at Microsoft have similar goals in that they automatically cluster and label activity resources and detect office activities. Next, managing lots of activities is hard for one person, and it's even more challenging when you add lots more people to the equation. Solving this problem will involve facilitating group coordination and awareness at the activity level. So for example, this could be really enhanced by an awareness of when colleagues are working on an activity, what shared resources have changed, and any changes to the group's schedule that could change an activity's priority. Both peripheral displays and glanceability will be important to accomplishing this without causing information overload. Another hard problem is to offer these activity management features on mobile devices. What activity information is most valuable while you're mobile? How do we visualize it, and what interactions are needed? Fieldwork will be needed to answer these questions. Health is another area where an activity-centric perspective that puts together a holistic view of people's health is useful. Health applications would also benefit from ubiquitous computing, which is another interest of mine. People are busy. They don't often have the time or the energy to improve their health. If we can make health management easier to understand and more visible in people's lives, we may be able to lower the barrier to people taking control of their health. Some existing work is on sensing biometrics in exercise, for example, the Health Gear project here. Also motivating better exercise habits and getting nutrition information using mobile devices and barcodes, for example, the ARA project here. Some new approaches to this problem are to analyze and visualize exercise, biometric, and food nutrition information all together for a complete health activity system. Also, predicting and attaining future goals given past and current habits would introduce some interesting visualization problems. And in general, both focal and peripheral visualizations to improve awareness and motivate positive changes. And also, there are some other interesting areas within healthcare, like including enabling health service providers to communicate with patients and detecting potential health problems. In conclusion, my research has focused on helping people feel in control of task and information overload in their daily lives and at work. My past projects have looked at balancing privacy control, interruption costs, and valuable new location-enhanced services, helping the deaf feel in control of sound information without overloading them visually. And my thesis research provides guidance for designing and evaluating glanceable peripheral displays. My future interests include helping people feel in control of their many work tasks and also health-related activities. At this time, I'd like to thank you. Also, I'd like to thank the NSF for funding, and my advisor, Jen Mankoff, my thesis committee, which includes Mary, and all my past co-authors, which includes George and Desney, and welcome any questions you have.
Sorry. Your task that when I look at glanceable displays and the possibility of accessibility displays, I start to think about people who are working on something. Your task was very centered, obviously trying to keep the trackball within your spot. What about it? What was going on mentally though is one of the things that I worry about, and so I would say that one of the things was change the task in additional research, where the user was trying to absorb information and seeing how the glanceable displays interfered with their ability to pick up information. And there's a worry that you can see somebody's monitor surrounded by 37 displays, it's giving them different information. Their mind is never centered on the task that they need to be centered.
Yeah, that's an interesting question. My motivation in looking at peripheral displays was the idea that we're already being interrupted with important information. And it is important that we do get some of this information that's being presented to us from other tasks and from communication like email. But to strike a middle ground between an interruption and just turning off all the interruptions. To have something in the middle where users can control when they look at it and when they attend to it. So to have it be more subtle but also glanceable. That was the idea behind it, but it is an interesting question. Surely turning it off is going to be the best thing in terms of your primary task productivity.
Well, you could also, there's been some studies on fighter pilots.
They can't take off unless they turn on every system in the cockpit. But as soon as they take off, they turn off all the, I think there's 3 or 4. And the reason was
they didn't want to be bothered, right? They have a singular task, which is in the air.
Yeah.
And they only need to know if somebody's A, going to shoot them down, or what they're shooting at. That there is this quick realization that they had all these systems here that they really didn't care about. Their main focus was so central. And so that they still allow them to do that. And it's interesting because there's all kinds of warnings that go off in that. Good, thank you.
Thanks. Yeah.
So in your multitasking study, you said that you had 3 techniques, which was the scaling and the clipping and then the change detection, right?
Yeah.
You also said you had 4 display conditions in that.
Right.
And I think you collapsed across those 4 display conditions when you were talking about here. I wonder if you could talk a little bit about what those 4 display conditions were, and were there anything where, like, some display conditions favored one versus another kind of notification technique or whatever?
Right. Okay, so the 4 conditions were scalable fabric, clipping lists, scalable fabric plus change borders, and clipping list plus change borders.
Oh, I see. So the displays were actually...
Like just those particular...
Yeah.
So it wasn't really like a 3x4 kind of thing. It was just
2x2.
Okay.
Was there something else you wanted me to comment on?
No, I was just trying to understand what that meant. So in the clipping list, you said that the participants actually got to pick what they got to outline.
So actually, for the study, we set it up ahead of time.
Okay.
That was a little confusing when I said that. The use model for the system itself is that the users would select it for themselves if they were using this. But for the study, we wanted to control that people all saw the same thing. Exactly. So we selected for the study itself. Yeah.
So I've had a lot of trouble getting my head around clipping lists. I used a demo of a clipping list system for a few weeks in there and completely was unable to figure out what bits to clip and how and when. And your image of what a clipping list is isn't helping me any. I understand how an upload progress window works. What does documents to Excel mean, and what progress am I expecting to see there?
That's a good question. I think that if we were to build a system that was optimally designed for all different kinds of resources, like all the things that you use in an activity, we might use 2 different techniques. So for things that aren't updating, that you just need to recognize, we might use a different type of design than for things that are actually you want to look at, that are changing, that are updating. So
this is both for change and for activity awareness.
yeah, well, so there were 2 different, there was knowing when to resume, so know what's going on, but there's also being able to reacquire a task, which requires knowing what each resource is. And so being able to get back into a task means that you have to remember what you were doing, what different windows you were using for it. And so the idea is that the clippings, the document 2 or whatever, helps you to recognize what that is. So,
but your study was centered entirely around interruptions and changes in state.
We had some amount of recognition of windows as well. So for example, people had to upload those windows in order. So knowing which order to upload them in was helpful. Corey and then...
Okay. In all of your setups, in your experiment, you used a dual monitor display, which typically is used by people as being a fairly active working area. Have you looked at all if your glanceable peripheral display is really only for the purpose of glancing and very much on the periphery? Like what if you took that second monitor and set it over here or made it horizontal? Or in a different configuration where it wasn't actually being used as active space in the task? Have you thought about how that would change some of your design?
So you mean putting something farther in the periphery such that you have to explicitly go to that for information?
Yeah. And I'm assuming that, again, because it wasn't a real field study, people probably weren't using a dual monitor setup. But in the real world, in my dual monitor setup, I'm very much actively using both monitors. Where sometimes when I envision a glanceable peripheral display, I might think of a separate display that's sort of only used for me to glance and get additional information.
Yeah, I think that's an interesting area for future work for two reasons. One is seeing how people set these things up and actually use them, and the other is to see, is it different when it's not right there on your dual monitor system? Gina?
So for these kind of pending task peripheral displays, they're like the file download one. There are the changes that you want not to notice, that you want the display to change, because you want to be able to glance over it and see the progress, but you don't want to draw the person's attention by flickering stuff in their periphery. And then there are changes that you do want to draw attention to, like the file download continues, or the other person checked in document 2 if they were working on it, or whatever.
Yeah.
Have you thought at all about how to be able to sync some of the changes out of awareness and forward some of the things into awareness?
Right. Yeah. So my thesis work has primarily looked at the design and the glanceability and not at the attention capture issues. I actually tried really hard to separate those issues out to try and control for the glanceability issues. So that is another really interesting area for future work, looking at attention capture and what that means. And one of the pieces of the activity theory analysis we did was looking at different design dimensions of peripheral displays. And one of the design dimensions was the criticality of the information that you're showing. And the recommendation that we made is for different importance levels, you need to use different update mechanisms. You need to have something either that's going to capture attention or be more subtle. But I haven't actually done any studies that look at the mechanisms there.
Thanks very much, Tara.
Thank you.